Welcome back, folks. Let's look at some of the values that I introduced in the first video as they pertain to just a normal cosine here. Okay, so I have just a single cosine. It's similar to one of the ones, it is one of the ones we used in the previous video. Let's get that up on the screen. Okay, this is 4 at an angle of 0. So what we plotted here is 4 cosine 2 pi has the coefficient of t, and we have no phase shift, plus 0 degrees, and that's all. This one's not in volts, right? I didn't label that axis, so we can just call it x, lowercase x. Okay, it could be a voltage, it could be a current. If you're really going beyond the scope of these classes, it could be a force, it could be a moment, a velocity, anything like that. Okay, as long as it's a cosine or a sine. All right, so we looked at the vertical scaling a little bit. Okay, we can talk about it in terms of peak to peak. Okay, so this one, if we measure the distance here in terms of peak to peak, let's call it a voltage. I want to call it a voltage. It's just easier to talk about that way. So let's say this is V of t, and the unit is, of course, going to be volts. Okay. Back to a voltage. We can measure this distance. We start at 4 and we go down to -4. So that's a distance of 8 volts. And sometimes you'll see that as 8 volts peak to peak. Okay. Now, the voltage peak, we just take that and divide by 2. We can talk about it as 4 volts peak. Okay, so those would be 2 ways we can talk about the vertical size of this cosine. Okay, the other one is, I mentioned it, it's called RMS, and we would divide by root 2, which would give us a magnitude somewhere in the neighborhood of 2.828, and you'd see that sometimes as VRMS, and the convention, which I'm going to be bad about this semester, is if you don't have any subscript, you assume that it's an RMS voltage. Okay, why that is, I'm going to leave to another video. Okay, but that's the vertical. Those are the 3 values that I can pick off of this vertical. Now the horizontal scale, I said there's 3 ways to talk about that one. And all of them have to do with how quickly our phasor is rotating. So now that, after the previous video, I'm hoping you're more comfortable that this is a phasor that rotates. All of them have to do with how quickly it's rotating. So the first one that we can talk about is called the period. Okay, and it is a period of time. It's the period of time it's going to take that phasor to rotate around one complete time. So with this one, that starts with a phase angle of 0. It's going to complete one rotation. So it's going to go from its peak to 0 to its negative peak, back to 0, and then back to its positive peak. That's one full rotation, and we call that one period. Looking at the plot, it starts at its peak here. Okay, where am I going to draw this? I'll draw it. I can do it somewhere in the middle. Okay, it starts at its peak here. It goes to 0. It goes to its negative peak. It goes back to 0, and it goes back to its positive peak. Okay, so from here to here, we can call this distance, and it's a distance along the time axis. We can call that capital T, which is the period. Okay, capital T is our period. And we define that as the time it takes. You ready? The time. I can do better than this. I'll type it for you. It's the time it takes the phasor to complete one full rotation. So we measured in seconds. Okay, the unit is seconds. And that's how we're going to label it. In your head, I want you to remember that it's how many seconds it takes per cycle. Okay, So you can think about it as seconds per cycle, like that. Okay, let me get that definition typed up for you. Ready? Magical video editing. Ta-da! Okay, so it's the time it takes a phaser to complete one full rotation. Now, it's useful. We can see it on a plot, which means, more importantly, we're going to be able to see it on an oscilloscope when we start measuring these waveforms. But how does that relate to 2 pi? Okay, so in this case, we can see that if I call this, oops, here we go. If I call that T1 and I call this T0, that the period is just T1 minus T0. And in this example, that's going to be 1 minus 0. This is all behind my head. Let me scroll up a skosh. Okay, and it's going to be 1 second. Just for this example. That's going to change with different waveforms because it's all going to scale. Okay, so we went from positive peak to positive peak, and we found that we had a period of 1 second. Okay, so the next way that we can talk about the horizontal scaling is called the frequency. Okay, a word that we're all familiar with, but let's figure out what that means here. Now the frequency, lowercase f, is the variable we use for frequency. The frequency tells us how many times the phaser goes around a complete rotation in 1 second. Okay, so it's kind of taking the same concept and just flipping it. And that's exactly what we do here. We say the frequency is equal to 1 over the period. Okay, so where this value, the period, was in seconds per cycle, okay, this one is going to be in cycles per second. Unit, in this case, is cycles per second. Okay, if I invert the period, I'm just going to invert the unit along with it. Okay, so cycles per second, this one gets named after an old dead guy. Okay, Hertz. So you've probably heard this one before. If you look at your radio dial, if you listen to the radio anymore, who does that? Okay, you might see the unit Hertz, megahertz, kilohertz, things like that. Okay, and it gets abbreviated with a capital H and a lowercase z. Capital H to honor Mr. Hertz. Okay, so all it is the inverse. Instead of seconds per cycle, this one's going to be cycles per second. And when you see Hertz in your head, I want you to think about, well, in 1 second, I'm just counting how many times that phaser goes round and round. Okay, so let me get that definition for you. Okay, there it is. And, you know, if we want to convert between there, we have this. Of course, we can flip that on its head and say the period is just 1 over the frequency. So you can go back and forth with that. Okay, so in this case, oh, this one's boring. It goes around once in 1 second, right? So we can say that F is equal to 1 over 1 cycle per second, or seconds per cycle. Okay, so that's going to be equal to 1 cycle per second, which is known as 1 hertz. Okay, so this is, again, from our example of the waveform that we have further up the screen there. All right, so we have period and we have frequency, but we don't have 2 pi yet. And I said that when we're using phasor representations, the angular frequency is the one that we're really after. Okay, so here we have angular frequency. And it's similar, okay? We're talking about how quickly this thing goes around. But instead of talking about how many cycles it travels through in 1 second, we can talk about the number of radians it travels through in 1 second. Okay, so the unit in this case is radians per second. Okay, so that's the unit we're interested in with angular frequency, and the variable is a lowercase omega. Okay, so if we're interested in radians per second and we have cycles per second, okay, we can say we have some value f in cycles per second, and we want to get to radians per second, then we've got to multiply by something that converts our unit for us. So think about the dimensions. Okay, we want radians in the end, and we got to get rid of cycles. Okay, so to make this equal to 1, we have to figure out how these are related to each other, and we should know that from pre-cal and when we were learning about angles. And if we have 1 cycle, we should have 2 pi radians, right? And then cycles cancels cycles, and I get, oops, let's get back to that. I get 2 pi f. And the unit is going to be in radians. Is this behind my head yet? Nope. Radians per second. Radians per second. And that's omega. Okay. So omega equals 2 pi f. Okay. And we can flip that on its head and we can say f equals omega over 2 pi. So those would be the 2 conversions I'm going to do here. For our example, right, we know f is 1 cycle per second. So if we want to find omega, we say it's 2 pi times 1 cycle per second, or 1 hertz. Okay, let's go ahead and use the unit that's more common. And we would find that we have an angular frequency of 2 pi radians per second. Okay, so we have the vertical scale in volts peak to peak, volts peak, or VRMS. And then now that we understand that this is a thing spinning around, we can talk about how long it takes to make one complete rotation, how many times it completes a rotation in 1 second, and then we can also talk about how many radians it moves through in 1 second. Okay, those all give us some idea of how we're going to stretch it horizontally. Okay, now the phase angle is going to give me the horizontal shift this way. Okay, and what are we going to do with that one? I think we're going to leave that to another video. That's kind of its whole animal onto itself. Okay, so right now we can stretch it in both directions. Next video, we're going to slide it back and forth. All right, stay tuned and good luck, folks.